Thanks, Susan. Thanks, everyone, for coming. It's very much about econometric forecasting as something we apply to climate change. So I'll talk about both aspects. And the paper is jointly with Jenny Castle and Zach Miller. So we'll have a quick look at some climate data, a brief review of climate science and climate model forecasting, and then look at the implications of shifting distributions for forecasting, and then turn to actually forecasting climate variables 20 years ahead and draw some conclusions. So starting with data, here's the 800,000 years of Ice Age data showing the change in atmospheric CO2 over the period. And it goes up and down by about 25 parts per million in the atmosphere, where 1 part per million is 7,800 billion kilos of CO2. There are a few obvious events happening that shift the relationship. The Brunhes-Mathieu polar reversal, when it goes from the South Pole to the North Pole as being the magnetic attractor. Then there's this big issue of the mid-Brunhes transition as it goes from fairly stable, fairly short cycles, suddenly very unstable and much longer cycles. You can see the variance goes up quite a bit. Sometimes supervolcanoes cause an immense jump in CO2, and sometimes they don't because they put out more particulate matter than CO2, and sometimes they lower the temperature because that particular matter dominates the amount of CO2. But Taupo in New Zealand on this occasion raised Earth's temperature. But compared to what's happened over the last 250 years, all that variation looks absolutely tiny, 130 parts per million in virtually a blink of a geological eye. So could we have forecast this outturn? And it's make clear that climate change was not inevitable. Forecasting the jump from 1760 to now would have required you to forecast that economies continued to be dependent on coal and oil and natural gas and grow substantially, but worldwide to create so much. In turn, that would have needed to ignore the knowledge by 1900 that increased CO2 would cause a warming climate, and yet no counteraction was taken. And also, by 1900, climate change could have been prevented by discoveries about generating electricity and the inventions of solar cells, wind turbines, and electric vehicles with rechargeable batteries, all of which were available by 1900. So climate change was not inevitable, and making the forecast would be very conditional on a lot of events happening. So what determines the success of econometric model-based forecasts? Well, there have to be regularities in the system being modeled. Those regularities also have to be informative about the future. For example, stock markets are regularly modeled as a random walk. That's completely uninformative about the future. The estimated model has got to capture whatever regularities there are, yet exclude the irregularities that might swamp the regularities. Now, we know there are regularities in both climate and macroeconomic data. For example, a warming climate melts ice, raises the temperature of the oceans, and that raises the sea level. And these are pretty strong regularities, and they are informative about the future, and some of them are embodied in empirical systems. But even in climate, sudden unanticipated changes are not rare, can be large, and lead to forecast failure. And recent examples with substantial impacts on climate-related economic variables are the financial crisis in 2008, COVID-19 pandemic, Russia's invasion of Ukraine, and all of these tell us that the data we're dealing with is highly non-stationary. So if we look in more detail at monthly atmospheric CO2 levels measured at Mauna Loa in parts per million, it goes from about 310 to 420 over the period 1960 to 2020, where we start with the Keelings doing flask measurements that are accurate measures of CO2. And to show that the trend is changing all the time, I fitted a single linear trend, and you can see that the trend here, for example, would have been way out there if it stayed at that level, and the new trend here would be very much steeper than any previous trend. And that tells us that the annual changes in atmospheric CO2 in parts per million are increasing. That is, we're getting an acceleration in the amount of CO2 in the atmosphere, despite Paris and the other COPs attempting to slow it down. The one country that's doing the opposite is the UK, which is one of the most non-stationary time series imaginable, reasonably steady up till the end of the First World War, oscillating violently in the interwar period, recovering after the Second World War, going up, and then starting to go down and dropping very steeply in this century. So it's got extreme non-stationarity with trends in all directions. It's also true of global measures. The mean surface temperature deviations also have jumped around a lot, rising more at the last half of the 19th century, falling in the first half of the 20th, and then rising since, and going up much faster in the Arctic than globally. And that's because of the transit of heat from the equator to the Arctic once the planet starts to warm. Ocean heat content deviations also have been changing dramatically, slightly stable, rising a little, then rising very steeply. And note that even by the end, the rise is faster than the most recent trend that I've fitted here. And it goes down to 2,000 meters where it's also rising. That means that the ocean is absorbing a lot of the excess heat in the global climate. This, of course, is leading to global sea level rise. And again, we see the same thing. It has risen quite a lot, but the current rises are going even faster than any previous ones. And that's about 10 inches since 1880. And that will get a lot worse if we continue in this trend with much warmer climate. Again, if we'd estimated what would have happened in an earlier period, the trend would have been wildly wrong by 2020. The climate change is something that happens slowly, but a key feature of it is what is the trend doing and why are there trends to start with? So a common feature of all these graphs is non-constant change. Changes keep changing, sometimes accelerating, sometimes slowing, and occasionally dropping. And this makes forecasting very difficult as changes in the change are very hard to anticipate. Importantly, if it does change during a forecast interval, that will later become a break in sample, which will contaminate estimation of the parameters of the model unless they're properly handled. Now, what can econometricians contribute? We know that human behavior is the key determinant of climate change, burning fossil fuels, agriculture releasing greenhouse gases, so carbon dioxide is going up, so is nitrous oxide and methane, all of which are greenhouse gases. And these accumulate in the atmosphere and reflect back the radiation from the sun that comes in as light, changes to heat when it hits the Earth, and then gets reflected back as heat. Now, we're used to modeling aggregate human economic behavior, which is non-stationary from evolving trends and breaks deriving from pandemics, wars, technical progress, financial innovation, demography, economic policy regimes. And these all have impacts in the climate. So climate data is also non-stationary and in turn feeds back onto economic outcomes. And at the moment, that's especially through extreme events like wildfires, cyclones, floods, and droughts. But econometricians have tools for jointly modeling interacting systems of non-stationary time series, and that's what we can potentially contribute if we can do it properly. So let's have a brief look at climate science. It's characterized by very complex interactions between the atmosphere, oceans, and land, and these are influenced by natural forces like solar radiation, seasons, plate tectonics, volcanic eruptions, El Nino, and so on. There are anthropogenic factors from burning fossil fuels, land use for agriculture and forestry, dams to store water, and so on. And the consequences of their interactions: reduced albedo from melting Arctic ice, which means warming speeds up, aerosol pollution, which slows it down, and these cause changes in rainfall and cloud cover. We get wildfires, sea level rising from melting ice sheets, coastal erosion, and so on. The emissions from greenhouse gases from natural anthropogenic sources accumulate in the atmosphere, and that's why we call them greenhouse gases, because they re-radiate energy from the sun. So climate forcing refers to an imposed change in Earth's energy balance, And total radiative forcing is the sum of all forcings, whether natural or anthropogenic. The IPCC provides estimates of total radiative forcing from anthropogenic sources and natural forcings due to solar radiation and stratospheric aerosols from volcanic eruptions. But not all natural changes in Earth's energy balance are forcing. We've got endogenous natural variability with semi-periodic cycles like El Nino Southern Oscillation, Atlantic multi-decadal oscillation, the Pacific decadal oscillation, and so on. And changes in temperatures from such cycles have magnitudes large enough to temporarily offset anthropogenic forcing and cause apparent hiatuses, so making found policy analysis. And clearly, there's something that's seized upon by climate deniers. Oh, look, climate's not warming at all, but it's a very temporary offset to anthropogenic forcing. Measures of CO2, nitrous oxide, and methane show they're all rising very rapidly. And atmospheric methane is due to natural gas leaks, of which there's lots around the planet. Tundra's beginning to melt, putting out even more, both CO2 and CH4. Animal husbandry greatly increases nitrous oxide from artificial fertilizers, and increases in wildfires not only cause vast damage, they release carbon monoxide that nullifies hydroxyl-free radicals that, if they were still there, would help remove methane. So methane increases ever faster. Latest IPCC report notes that methane is responsible for about a third of the 1.5 degrees of global warming, partly offset by sulfur dioxide emissions cooling, with half due to CO2. Pandemic lockdowns reduced our greenhouse gas emissions, but the atmospheric concentrations increased nonetheless. So controlling GDP growth is not likely to get society to climate neutrality, as pandemic lockdowns are the biggest falls in GDP ever experienced by developed countries, and probably underdeveloped ones as well. So this plots the daily CO2 emissions in megatons, not megatons, not parts per million, so absolutely tiny. And this shows how much more they dropped during the pandemic. But even at their greatest relative to what they were before, we're only talking about 30 megatons, absolutely tiny. And by the end of 2020, we're back where we were. So it's absolutely hopeless to rely on GDP reductions to get us anywhere. So climatic outcomes depend on the physical properties of energy balance and our human behavior. The time series non-stationarity is due to inertia. What happened today is very similar to what happens tomorrow. Stochastic trends that you've seen and distributional shifts from changing means and variances over time. The forecasting the change is much easier in climate terms of what it looks like, but it's insufficient as many features of climate change depend on levels of variables like the atmospheric CO2 content, which requires accumulating the forecasted changes to levels, if that's what you're forecasting. So a reasonably accurate forecast of a change may accumulate to poor forecasts of levels. An average growth rate of 2% per annum is forecast by 1.6% per annum after 5 years, out by a whole year relative to what is actually going on. Now, most excess energy is stored in the climate system by being taken up by the oceans, which leads to thermal expansion and sea level rise, and that becomes baked in because it's a very slow adjustment to past temperatures. So the forecasts of serious coastal flooding are reliable. Possibly up to 1 billion people may be flooded by the end of this century. Now, the outcomes differ across representative concentration pathways, RCPs, and would be much worse if West Antarctic Greenland ice masses melted faster, which Luke Jackson and co-authors show they're actually co-integrated I2. The contribution from thermal expansion to sea level rise is very substantial, and storm surge heights depend on local conditions, and the resulting damage even more so. But sea level rise will intensify coastal flood risk by changing the amplitude and occurrence of storm surges. So if we look at the return periods, these are based in Sheerness and for London. We look at the water level above the local measures. We look at this increasing present flood level curve, depending on how long a period we're looking at. if there wasn't climate change, and this is what they predict will happen, with this amount being the sea level rise. So if we look at a 1 in 500-year event, which flooded by about an extra meter over what you would have expected otherwise, it becomes a 1 in 20-year event in the future, just drawing the line across at that level. And that's pretty disastrous. These were very bad floods when they occurred, and now they're going to occur every 20 years. And if sea level went up, it would be even more. And big floods that occur occasionally will be much higher, again by almost a meter more. So the magnitude of storm surge return periods increases dramatically, and the return period reduces dramatically, about 1 in 20. This is because of the non-linearity of the relationship. And long-term storm surge records and forecasts of sea level rises are fairly accurate. They've been made for many years because, of course, shipping has always been important, and many harbours had incidental tide gauges. That is, people just watched what happens and recorded it. So the predictions are fairly reliable, even if we don't know the exact dates. So here it would be about 74 centimetres from RCP 8.5, which is the business as usual one. There's a 1 in 500 flood shifting to 1 in 20, so it's 25 times more likely to occur, and it would increase by that amount. Forecasting the relevant local sea level rise, the main contributor is the forecasting returns periods and magnitudes, but it also matters what the wind speeds are and whether it's a spring tide or not. So these are slightly harder to forecast. But return periods for weather phenomena include inland floods, droughts, heat waves, max day and nighttime temperatures. So it's quite a useful tool to master. Now, the complexity of physical climate models has grown with computing power, based in energy budgeting, first law of thermodynamics. So the first generation were called zero-dimensional energy balance models, and they equated global temperature changes to proportion of the difference between incoming solar energy and outgoing energy re-radiated by the Earth. And of course, that's what's being changed, because the solar energy coming in isn't much altered. In the 1960s, one-dimensional models explicitly covered horizontal latitude net heat transport, and then 1.5 to 2-dimensional models allowed for both horizontal heat transport driven by more complex forces, so temperatures varied over both latitude and longitude. However, these early models either omitted anthropogenic components entirely or had stochastic forcings that were weakly stationary, but anthropogenic forcings are not stationary, so one can't trust the results from such models. Climate scientists now produce simulations of an underlying physical climate model, often tested against ice age data, and conditional forecasts are made with certain anthropogenic scenarios in mind. So they're produced by global climate models, are high level of complexity and spatial temporal disaggregation. And if you look at the RCPs, they focus on concentrations of greenhouse gases rather than emissions, which is correct. And the shared socioeconomic pathways expand in RCPs by allowing for alternative scenarios in economic and population growth. There's a lot of uncertainty around the initial conditions of climate models, and slight mistakes in the measured state of the atmosphere can grow rapidly over time, leading to large errors in the future. This is the so-called butterfly wing phenomenon. Ensemble forecasts, computer model run a number of times from slightly different initial conditions, are used to estimate uncertainty around the central forecast, but that makes many other hidden assumptions that the central forecast is itself fairly accurate, which need not be the case, even when you assume what the future path of greenhouse gases would be like. And that, of course, is highly uncertain. It's dependent on human use of fossil fuels and agriculture, so the projections conditional on concentration pathways rather than unconditional outcomes seriously underestimate the uncertainty in the future climate. In any case, the interpretation of uncertainty from climate models differs from that of economic or statistical models. It's based on a common set of input data, but different models and different initial conditions, whereas we're calculating uncertainty, assuming the model's known, but the parameters are unknown and estimated, and there's an error specification for the unobserved determinants. Both are a bit impure, but that's what we do. So the alternative to combine model output to assess future uncertainty with statistical emulation of global climate model output uses classical statistical methods. Pattern scaling maps spatially disaggregated temperatures to global mean temperatures, and spatially disaggregated models constructed by mapping spatially disaggregated temperatures are mapped to a common spatially aggregated anthropogenic series of climate forcings. These are called quasi-representative concentration pathways and can be created that mimic the pathways that result in these giant global greenhouse gas concentrations from global climate models in a target year. And Earth system models of intermediate complexity aim to capture the most important features of global climate models, yet can be run quickly enough to assess uncertainties through multiple runs and to produce results in a policy-relevant timescale. The class that's often referred to as integrated assessment models, and the complexity of those has grown over time, though not as much as global climate models. But you can couple integrated assessment models with these mimic models and allow for a model-consistent framework to assess economic and climate scenarios and the resulting policies. So climate impact studies require sectorally, spatially, and temporally disaggregated data. And many empirical model studies actually rely on model outputs as data rather than observational data. We tend to think about measurement error in observational data, such as those that lead to revisions in GDP. But with climate data, the entire time span may be subject to revision when new methods are found to address known measurement errors on the computer-generated systems, because, for example, a new model of cloud cover is introduced, and suddenly you get a very different trajectory historically as well as currently. Although availability of satellite and other high-resolution data sources are available, missing data are pervasive in the historical record, and model output data can be obtained at virtually any resolution, but should not be used directly. And there's several articles explaining how they need to be bias corrected using what we know from history about climate data. Now, there are direct links between climate models and econometric systems. So, for example, co-integration has been applied to climate systems by David Stern and Robert Kaufman and others since then. Energy balance models of global temperature, ocean heat content, and radiative forcing equivalent to co-integrated estimate systems and estimated from discrete time data by Felix Brettes. And estimated parameters quantify uncertainties in integrated assessment models of the impacts of climate change, but could have very large variability. So accounting for structural breaks from volcanic eruptions highlights parameter uncertainties, as previous estimates of temperature response to increased CO2 concentrations may be too low, because volcanic eruptions, on average, lower temperatures by putting out more particulate matter to block sunlight than CO2 to increase temperature. Recently, moist energy balance models allow for horizontal net heat transport and are equivalent to a co-integrated system, and they show that there'll be more warming near the poles than the equator, which you've seen from the data is correct. Most climate econometric time series analyses don't actually strictly impose energy balance properties, allowing for measurement errors, etc., but do seek to be consistent with conservation of energy required by the first law of thermodynamics. So let's look at the implications of shifting distributions for forecasting. Statistical forecasts confront many issues. So why would you want to use statistical forecasting methods for predicting climate? First, the horizon is traditionally much longer than we're used to in economic forecasting. For longer horizon forecasts, non-stationarity plays a key role and can take the data far from where you would see, as I showed in the very first set of graphs, 130 parts per million in 250 years dwarfs what was happening over the ice ages. Breaks in trend over the forecast period may be inherently unpredictable, depending on exogenation shocks like wars and distance policy changes when governments suddenly ban things like using coal or driving petrol and diesel vehicles. But conditional forecasts based on assumptions regarding future policy and events are feasible. You just don't know which conditional forecast will be of interest. So a key feature of forecasting models is whether they are closed, as we will work with shortly, or open. Some variables are unmodeled, and conditional forecasts are made, as with global climate models. That means that the exogeneity of conditioning variables matters concerning linking economic outputs to temperature, as there's a big literature, or the opposite, linking temperature to economic outputs. They both cannot be correct, as Felix has pointed out in some of his research on exogeneity. And finally, the invariance of model parameters to policy interventions and environmental changes is crucial, and there's almost no research on how invariant model parameters are when things change, like banning coal, how invariant were the system in climate determination in the UK. So I want to quickly walk through the difficulty of dealing with trend breaks. So the data generation process, a very simple random walk with drift at 1% per annum. So it's going up and down over time. But we then shift down the growth rate by just 0.1%. That's pretty tiny. And it happens at t equals 100 in this 200 long time series. And you can see the slightly different outcomes, but they're almost indiscernible to the naked eye. We accumulate the growth rate before the shift, and then we add in the shift at the breakpoint at 100. It's only actually really detectable after about 10 years that there has been a change. So if you were forecasting from here, you wouldn't know for 10 years that your forecasts were going to be very badly out in the future. Now, if you know the break and you fit from the break point, knowing how big the break was, it's reasonably good. It's not fantastic, but all the forecasts are well within the forecast confidence intervals, which, of course, for a random walk are pretty large and growing rapidly. If you ignore the break, funnily enough, what's happening before the break, this is 10 periods after it, and then the break coming in leads to forecasts that are wildly wrong, far, far too high. And we'll see that happens with some of the climate forecasts below. So it's not something that's imaginary. It's quite a serious problem. And you get increasing forecast errors for the next 90 years. The climate change is not happening at a constant rate, so we have to handle the non-stationarities caused by shifts and breaks, as well as smoothly varying deterministic functions. Arctic ice covers disappearing at increasingly rapid rates, accelerating ocean heat content and global sea level rises. Deterministic trends shown in plots are descriptive, not components of the DGPs. They're reflecting responses to increasing atmospheric levels of greenhouse gases and changes in dynamics, as well as location shifts like impacts of the COVID-19 lockdowns and economic outcomes affect the greenhouse gases. Now, little can be done when the anticipated shifts occur after you've made a forecast. Imagine forecasting at the end of 2019, just as COVID was starting in China for 2020, you'd be vastly wrong. But they're difficult even when the antecedents that might predict a shift, that is, information going beyond the relevant disciplines information on regular forces, e.g. advanced warning of El Niños, because it's still very uncertain that this unanticipated shift will occur. So if we look at the distributional shifts in monthly global atmospheric CO2 that have occurred, they're all over the place, but they're all going in one direction. And the most recent ones are the most extreme shifts, dwarfing the earlier ones. So we have to do something if we're not going to have runaway climate to stop the parts per million of CO2 in the atmosphere, which of course are being enhanced by methane and nitrous oxide. So we've got to tackle energy generation, and that is currently the best where we are. We could produce a lot of energy from green sources like wind and sun. Construction, there's quite a lot of movement in reducing greenhouse gases in construction, going back to Roman technology of 2,000 years ago. Chemicals, not much happening there. Artificial fertilizers, a lot of them could be replaced by basalt and biochar. Deforestation, we could tax countries that are deforesting and pay them to save their forests, and agriculture, cutting out a lot of the methane that animals give off by trying to introduce methane, anti-methanogenic bacteria from things like seaweed. And waste, we could try to capture the methane given off. But these have happened. There have been lots of breaks. We use indicator saturation estimators to detect outliers, shifts in mean or in trends, because we don't necessarily know at which point in the data sample happened, and we can't rely on knowledge of their numbers, signs, magnitudes, or timing. So the principle involves generating an indicator variable for every observation in the sample. We add that to the set of regressors to search for their significant. So we could have impulse dummies, which are 1 at one observation and 0 at all others, but there's capital T of them. Step dummies, which accumulate impulse dummies. Trend breaks, which accumulate step indicators, or multiplicative dummies that interact step indicators with the regressors in the model. Now, you can't add all indicators at once. That results in a perfect fit and is completely useless. But you can use pre-search algorithms with expanding and contracting block searches to allow for all possible indicators to be investigated. So I'm going to look at trend indicators as ones where we're going to find major breaks in trend, which accumulate the step indicators. There are many, many equivalent forms. The ones we use to find the final trend is starting at -t and going up to -1. That's how it's implemented in Jürgen Dürnich's Autometrics program. Now, when you're selecting step indicators, you can retain all the conditioning variables without selection. They're just there in the background. So what you're picking up are the breaks in trend that aren't modeled by changes in the variables in the model. So these are things that if you didn't do trend indicator saturation, would be contaminating the model because they're not detected by the variables. Now, the trend indicators rapidly become very highly collinear. Imagine t-1. Well, it starts at t-1 up to t, and so almost all of the variable is in common. And their orders of convergence differs from usual root t to 1 upon t to 3 upon 2. However, the split half approach that we advocated many years ago, add the first half indicators and record those that are significant at some significance level alpha, say 1% or 0.1%, drop them and put in the remaining set of trend indicators, again recording which are significant in that subset. Now notice what you're doing here. Providing the Zs aren't very large, i.e. nowhere near half the sample size, testing for these is a perfectly standard regression. They happen to be trending, but that we know how to deal with by orders of magnitude. And so conventional statistical theory applies here, it applies here, and when you combine and test the recorded indicators from the two stages, it applies there. So there's nothing strange, in fact, about doing all of this. So to illustrate, let's look at some simulation data where the variable we're interested in depends on an intercept that might shift, a coefficient of the z that might shift, and z depends on an intercept, a trend, and an error. And we'll have the intercept at 10 over the period up to 60, and then -50, and the beta 1 at 1, and then it goes to 2 over the remainder of the sample. We set sigma squared v tiny so that z is actually looking like a deterministic trend. So you can see the trend break that comes about from shifting the parameters. It's rising here and it would be there, but it goes up. But it's quite difficult to see in the changes. Yes, if you know to look for it, you can see these are a little bit higher than those, but of course there's no change in the z's. So if we include the first 50 indicators, test for the significance, we don't find any, so the model's what you'd expect. Then the second set of indicators, well, actually it does find one, t at 64, which does appear to be a slight change even under the null that the model is constant, and it doesn't have much impact. But when you combine them, so instead of testing this in 50 observations, you're testing it in 99 observations, it's not significant. So the correct model is found in this instance. Now there is a trend break at 60, But when we put in the first 50, they don't find anything. And you can see the trend break here, and yet it's not picked it up. But in the second half, amazingly, it picks up T of 64, showing something was happening even under the null at that, because this is not the right number. The break was at T of 60, so it's slightly late in picking it up. And if we combine the two, it still picks it up. And so we get a slight wobble around here. It's 4 observations away from the actual data generating process break. Now, if we use tight significance levels, we avoid the problem that at 5% under the alternative, 11 indicators are picked up. They do actually catch the break, and only 2 are retained if you jointly combine them, but it wobbles a lot, and both trend indicators are picked up, and they're at the wrong place. So at 1%, you get these wiggles. At 0.1%, you still get a shift, but much more certain about where the shift is. And at 0.01%, you only retain the 1 indicator at 60 this time. So it does pick up. That is the break. It's the most significant of all the trends, and it picks it up correctly. So it's very important in multipath searches for trends to use very tight significance levels. So forecasting using this, if we don't use a tight significance level, the root mean square error is 2.88. At 0.1%, we retain the 2, and it goes down to 0.97. And at 0.1%, it goes down to 0.89, and is very much correct. But the smaller changes are hard to see in delta y. So if you don't allow for any changes, you just fit a constant, you get these residuals. If you fit it 0.5%, you pick up a spike and a shift in the mean. And if you analyze at 0.1%, you pick up the mean shift, which is due to the change in trend being difference. And so you get that outcome. Now, what I want to stress is when forecasting in differences, you really have to accumulate to levels. So if we're forecasting in differences and we don't do step indicator saturation, the in-sample base for the forecasts gives a root mean square forecast error of 1.2 for the differences, but it gives 4.4 for the levels. If we use 0.5%, the root mean squared forecast error for the differences is 1, and it's 1.2 for the levels. And if we go to not 0.1%, then the root mean squared error is just under 1, so it's almost the same as these, but the root mean squared forecast error is dramatically lower at 0.7. So though these are all sort of looking alike around 1, 1.2, they're very, very big differences in the levels root mean square accuracy. So forecasting global CO2 using a univariate model where we're going to deal with trend breaks. This is what it looks like. These are logs of CO2. There's an explosive route over 1862 to 2018, which Felix and I explain as being mismeasured, combining 2 very different measurement systems. It's very hard to believe you get this big drop during the Second World War in CO2 emissions with all the oil fires and things like that going on. And you can see it's, once Keeling comes in, there's quite big fluctuations year on year from all sorts of natural factors. But rather than exclude the earlier sample, we use saturation estimators to try and handle the measurement errors. So if we assume constant parameters over the whole period, we get a model which fails every possible diagnostic test, and the forecasts are just like the ones I told you you would see. We're not modeling the trend, and it forecasts 680 parts per million by 2100, in line with the White House Initiative on Climate Change business as usual path, CO2 concentrations to exceed 700 parts per million by 2100. But it's a misspecified model, and these are, in any case, the wrong confidence intervals. So if we apply both impulse indicator saturation to pick up the blips that you saw in the graph, and trend indicator saturation, which picks up 2 trends, one showing that it was lower before and higher after, then we get a very different pattern. This is what it predicts. Actually, it's in line with the RCP 4.5 of 540, parts per million. The confidence bands for both models just reflect the association and the uncertainty associated with the specified model. So we tried mimicking what climate scientists do by estimating trend growth by going back 12 years and picking up the t minus j up to t, where j equals 2 to 12, and then averaging the forecasts and levels. And what happens here is really quite interesting. It's very bad. The forecasts are almost the same as the ones that don't bother modeling the trend shifts, and are way different from the ones that pick up the trend shifts and the outliers. So what happens when we try to model the climate variables? So we're going to forecast a vector of variables denoted by YT of atmospheric CO2, global temperature, ocean heat content down to 700 meters, and sea level. We're going to fit it from 1860 to 1960 to 2018. So I'm dropping all the probably contaminated observations before we get the Keeling CO2 measures. And we express it as YT depends on up to 5 lags, that is 5 years of feedback, and large numbers of possible trend shifts. So the var is extended by testing for trend shifts and restricted to significant variables in each equation, and finally expressed as an identified simultaneous equation system with contemporaneous interactions. So first of all, select trend shifts at 0.01%, i.e. 1 in 10,000, keeping all other var regressors. And that finds 2 trend breaks, 1991 and 2003, which are significant on the system test. This is not the individual equation test, but the system test. The lagged variables are then selected at 1% and reduces to 4, leaving 19 variables in each equation. Regressors in each equation that are insignificant at 1% are eliminated individually, and the resulting highly restricted system, all retrained variables are significant at 1%, both in individual and system tests. And this allows contemporaneous variables from every other equation introduced into every equation without losing identification. And this is something we can automate once you can go through this sort of procedure. And only 2 contemporaneous variables are significant, which results in a simultaneous equation model. So this is what we find for the simultaneous equation model. CO2 depends on CO2 lagged. Current temperature is a very significant coefficient. Sea level, 2 years before. The 2 trend breaks, 1991 and 2003, both of which show that CO2 is going up more rapidly after 1991, even more rapidly after 2003, and an overall trend. So these stop at the year that's shown. So they leave the trend break being the overall one that dominates into the future, having corrected it in the past. So these pick up what an investigator at the time would have thought the trend was. If you accumulate that 0.25, add it to t, you get 0.35. That's what you would have found if you're an investigator in 2003. Now, temperature depends on temperature lagged once and 3 times, and that cancels, of course, there's no unit root there. CO2 lagged with a positive coefficient, so we have positive effective temperature in CO2 and temperature, so it's a runaway system. On ocean heat content, sea level, just one of the trends and the overall trend. Ocean heat depends on the level of CO2, offset a bit by temperature 3 periods earlier. So this is picking up more than the total amount of heat that's generated by CO2. The ocean heat 4 years earlier, sea level rise, and again, the 2003 trend and an overall trend. And finally, sea level rise does depend on temperature, as you'd expect, positively, CO2 negatively, ocean heat negatively, sea level a couple of years earlier, a trend and the other trend, both of these, and an overall trend. Likelihood ratio test of over-identifying restrictions is satisfied. No system vector diagnostic test is given at 1%. For autocorrelation, arch, non-normality, heteroscedasticity, reset at nonlinearity, and our nonlinearity index test. And the only noticeable correlations between CO2 and temperature, possibly between temperature and ocean negatively, and ocean and sea level rise positively. So the positive effect of temperature and CO2, positive effect of CO2 in the ocean level, and feedback of temperature on temperature from CO2 lagged. Negative coefficients showed atmospheric CO2 and sea levels were increasing more slowly earlier than can be explained by the other variables, whereas temperatures and ocean heat were rising faster than can be explained by the other variables. But given the positive feedbacks without controlling the levels of atmospheric CO2, the system will simply spiral ever higher. This is a plot of all the eigenvalues of the dynamics. They're sort of around about 0.8, it's the closest to a unit root. So the non-stationarity is coming from the approximating trends and trend shifts. So here are our climate forecasts to 2038, and I've put in brackets what it would have forecast to 2108, but it just goes on and on. So this is CO2 forecasts, and it's going to predict 454 parts per million for 2038. And that's going to lead to a rise in temperature up to 1.34 degrees beyond where we start in this plot. It isn't the way that it's calculated when people talk about keeping below 1.5. It's an anomaly. And you can see again that it's reasonably well forecast. We don't know how it's going to turn out, of course, but the confidence bands aren't large. Ocean heat to 700 meters is also going to rise quite a lot, 26.7 joules, but it's going to be dramatically higher by 2108. And the sea level is going to rise by another 11 inches. Sorry, going to rise to 11 inches from where it is, and that's starting off at about 5 in 1960, but it would rise to 20 inches by 2108. Now, we're often asked, why do we model it in levels when log CO2 is the key determinant of atmospheric temperature? And it's because over the range since about 1960 to today, it's very, very hard to tell the difference between them when you scale them to the same units. And to show that, I've put in this graph, it's slightly hard to see, but this graph plots both the forecasts of CO2 and the derived forecasts from the log CO2 to put them into the levels units by taking the exponential. And you can just about occasionally see there's a slight difference between them. But for the two variables, CO2 and ocean heat, you can't see any real difference between them. So how does the forecast compare to naive forecasts? Well, that's the one from the original log CO2 model in units of CO2. That's the one from our system, and that's the one from the univariate model with a trend. So it kind of lies between the two extremes from the univariate model. So what conclusions do I draw? But I think econometric methods do have a useful role in climate modeling. Outcomes are determined by human behavior interacting with the climate itself from the physical properties. And that's very important because we have lots of experience in modeling human behavior in the economic context. And that's also true of it being used in sociology and political science these days. They're often using exactly the same methods. The time series data is non-stationary from stochastic trends and location and trend shifts. These make forecasts very uncertain and prone to failure, but they're the best we can do under the circumstances. Unanticipated changes cannot be avoided for the obvious reason that they're unanticipated, but later they become in sample and you begin to see their impact. So modeling must take account of them to avoid distortions in parameter estimates and the resulting forecasts. So they don't actually directly affect the forecasts. They affect the forecasts through parameter estimates you get by taking account of the distorting influences of unmodeled changes. So climate change is not a given, it's an anthropogenic outcome. We can still get to net zero greenhouse gas emissions by 2050. Jenny and I have written 2 papers on how the UK can do it and how developed countries in general can do it. But the speed and form of such transition will impact on climate forecasting if governments did ban the use of oil, as the Stop Oil wants them to. It would hugely change UK's greenhouse gas emissions. And therefore, any forecast based on the models I showed you, and we did model it and forecast it in an earlier paper, they would be badly wrong, but badly wrong for the right reason. The example I always give people to remind them of why they shouldn't worry about it being badly wrong is you take your car to a garage and the mechanic says, oh gosh, your brakes are about to be inadequate to stop you in a sudden emergency stop. So you say, okay, change them. So the mechanic changes them. 2 days later, you need an emergency stop, and it's quite successful. The car stops. You don't go back to the garage and say, why did you make me change my brakes? The car stopped perfectly well. That's the stupidity that you'd get if you complained about the fact that our forecasts went wrong. They went wrong precisely because they've been used to try and stop them going that outcome. And thank you, Susan. It's Susan's last day working for INET, and she has done that for a long time. She's kept the management team in order. She's organized these seminars over quite a long period and done a wonderful job in keeping the whole show on the road. So thank you, Susan.
Oh, well, thank you very much, David. That's very kind. And thank you very much for giving the final seminar that I'll be running. Thank you very much indeed. I'll take the focus back from me again. And has anyone got any questions from David's talk? Please just unmute yourself, raise your hand, go ahead.
Hello, can you hear me? So I actually had a question that's not necessarily specifically related to economic modeling, but I was interested to hear your opinion, David, on the degrowth or like post-growth movements that are gaining popularity recently, because you seemed, I guess, quite dismissive earlier on in the talk when you said that controlling GDP growth is not likely to get society to climate neutrality because the atmospheric concentrations increased even if greenhouse gas emissions reduced. But I suppose somebody who might be arguing for the post-growth or green growth ideology might say that a recession is kind of different to what they're talking about. And I was interested to hear what your opinion is on that kind of ideology generally. And thank you so much for such a great talk. It was really interesting.
Thank you. If we go back to 1840, when the first solar cells are invented, when we get solar panels that can go on roofs, when we get wind turbines that generate electricity, when we get renewable batteries, we could have had the same level of growth without any climate impact from 1900 onwards if everything had been done through electricity rather than through coal and natural and oil and eventually natural gas. And of course, once we start down that route, you can see all the technological developments that have been happening very rapidly recently would have happened 100 years earlier. We had the same amount of knowledge about electricity then as we do now. So it's not that it's GNP or GDP growth that's doing it. It's what we're using to get that growth. And we're using the wrong things if we want a climate that's stable, namely coal, oil, and natural gas. Now, we can't eliminate it immediately. Britain's eliminated coal from the energy generation system almost immediately without most people noticing, and it had nothing to do with the high price of electricity after the Ukraine invasion. And it will eventually produce electricity at a much cheaper and more stable rate, but it requires a big investment in a resilient and much, much larger national grid system so that it can supply cars. Cars can then act as storage units. We can get rid of diesel and oil and petrol-driven cars. They're much more efficient because petrol-driven and diesel-driven cars waste a huge amount of the energy and heat, as well as pumping out nasty gases. So I don't think we need to worry about reducing GNP. Rather, I think it actually could increase GNP quite a bit by producing new jobs for people working on all sorts of things, from heat pumps, solar cells, wind turbines, their repair. There's an article today showing that Germany's wind turbines are all getting very old and need to be replaced. Well, that's a huge amount of investment needed with all the equivalent jobs. And of course, it will show up as an increase in GNP, which at the moment Germany could actually do with. So no, I'm not at all keen in trying to reduce output. We saw the effects of the lockdown. There's a massive drop in GDP, and it created a great deal of hardship for the groups of people who were not included in things like the government's schemes for hidden employment, etc. Is that any help?
Yeah. Thank you so much for answering.
Thank you. Any further questions at all? No, it seems like you've covered all points there, David, I think. Fantastic. Well, we'll be posting the recording up to the website, and so everyone can review again later if they wish. But yes, thank you very much, David, and thank you again for the message, and thank you for the previous seminar. Wonderful.
Thank you.
Thank you
Thanks,
then.
Susan.
Bye-bye,
Best of luck in
everyone.
your new job.
Thank you. Bye, everyone.